Okay. Hello, everyone. Okay. Good morning, all of you. So, first of all, Happy New Year to all of you.
Thank you, sir. Wish
Okay.
you the
Yeah,
same.
so
Thank you, sir.
thank
Wish you
you.
this.
So, we are starting in the new year. Hope everything goes well and we enjoy. So, as my usual habit, we start with a quote of today. When life gives you 100 reasons to cry, show life that you have 1,000 reasons to smile. Because always there are in every life, it's not completely positive or negative or completely everything will be happy or sad. Okay, there will be situations where you are happy and situations where you are sad. So it depends on whether you want to be happy now or not. Okay, there may be 100 reasons to cry, but you have to see 1,000 reasons to smile. Okay, and we see who are the birthdays of today, and one is Robert Whitehead, and he is inventor of torpedo. I don't know how many of you have seen or heard about torpedo. So it is a missile which is fired into or out of the water. Okay, so because actually I worked in NSTL DRDO labs, Naval Science and Technological Laboratory in Visakhapatnam, where the main work is on torpedoes. Okay, and anybody knows how a torpedo goes?
It pushes the water behind using electrical subsystems.
Okay, electrical thing, how it gives the thrust?
It's like a propeller.
Yeah, but one thing is, if there is a propeller, what happens is after some time, the whole torpedo also will get the rotation. Did you understand what I'm telling?
Yes, sir. Counter rotation.
Yeah, there will be two propellers, counter-rotating propellers. It's similar to why we have two propellers for a helicopter.
Helicopter.
Yeah, yeah. In the same way, here if you see in the figure, there are two propellers. Okay, they are counter rotating, one rotating clockwise, another rotating anti-clockwise. So because there will be uh, both forces, and so this rotating force, it gets compensated by the other, and the thrust you will get. Okay, so he is British engineer who invented the modern torpedo. He was the first to produce an effective subsurface self-propelled torpedo. It was improved on the spar torpedo used during the American Civil War, which used a charge triggered by a long pole and floated to its target on a small boat. And Whitehead's first torpedo lacked speed and range. However, by 1870, he had increased its speed to 7 knots, able to hit target 2,100 feet away. The following year, the British Navy purchased Whitehead's invention, and Whitehead's torpedo was propelled by a compressed air engine and carried 18 pounds of dynamite. Its most important feature was a self-regulating device which kept the torpedo at a constant preset depth. And Edison made a movie of a Whitehead torpedo launch. And there is another important celebrity, and she is Savitribai Phule, and she is considered as mother of Indian feminism. And she was an Indian social reformer, educationalist, and poet from Maharashtra. She is regarded as the first female teacher of India. Along with her husband, Jyotirao Phule, she played an important role in improving women's rights in India during British rule. She is regarded as the mother of Indian feminism, and Phule and her husband founded the first Indian girls' school in Pune in 1848. She worked to abolish the discrimination and unfair treatment of people based on caste and gender. Okay, today we will have the first class on CFD, and we'll have introduction to CFD. Okay, before going to that, I like to have just look at all the people. Okay, can you people just show yourself and tell 2 or 3 words about you? And if you don't come by yourself, I will call by names. Okay, maybe in the order. Vikas, I think you came first also into the class.
Yeah, hello everyone. My name is Vikas. Uh, I live in Warangal.
Oh, local.
Yes,
Where? Where?
Vadapalli, sir.
The near, very near also. Huh?
Yes, sir.
Okay, okay, good. What is your father?
Sir,
What is your father?
my father, he is a private teacher.
Okay. So you stay in apartment or own home?
Own house, sir.
Okay, good. Okay, yeah. Tell me about your guide and project. At least something to talk. Okay, you are for third year. Okay, there will not be project. Okay.
Yes.
Okay, tell me your interests.
I like sports, sir.
Okay, which sport?
Cricket and football.
Okay, good. Participate or watch?
Participate, sir.
Okay, good. Can't you show your face?
Sir, no camera.
I'm not camera. Okay. At least sometime I think we can talk in WhatsApp. Hmm?
Okay, sir.
Okay. Thank you, Vikas. Gamsi?
Sir, yes, sir. I'm from Vizag. Uh, we had to introduce already known people, sir.
Okay. Hmm. Okay, Mahendra. I think A section people sometimes I talked now or there. Then Mahendra is there. Okay, Jayant Gaud also I think is not there. And Charan K.
Hello, sir. Hello, sir.
Yeah,
Um, can you see my face?
yeah.
Yes, sir. So I'm from Hyderabad, sir.
Okay. So where do you stay in Hyderabad?
Near BHL, sir.
Okay, right.
Uh,
That is after Kokatpalli and all. Huh?
yeah, after Kukatpalli.
Yeah.
You can call it Lingampalli also.
Yeah,
After
yeah,
next to Lingampalli.
that yeah, that local train ending or something, right?
Yes, sir. Yes, sir. MMTS.
Yes,
Yes,
MNTS.
sir.
Yeah. So what is your father?
He works at a private company, sir. Niehoff. He works at Niehoff,
Okay.
a German company.
Any interest?
Interests. I watch. I mean, I play cricket and badminton, sir. Those are my main hobbies.
Okay, thank you, Charan.
Thank you, sir.
Sai Rohan is there?
Yes, sir. Good morning.
Hmm.
My name is Rohan. I'm from Vizag.
Okay. Vizag, which place?
It's near Madhodara, sir.
Madhadar. Okay.
Mm. Yeah, yeah, that's it.
Okay, what is your father and what are your interests? Just you tell me.
My father works in the Navy, sir.
Okay.
Like he works on making torpedoes and stuff. He manages.
Okay. Yeah, right.
Yeah, my interests, I usually play games. That's it.
Master gamer, sir.
All rounder. Huh? Okay.
Okay, sir.
Okay. Thank you, Rohan. Zalika?
Good morning, sir. I can't switch on my camera.
You are in A section only,
Yeah, I'm in A section only, sir.
but somehow I am not familiar. Okay. Uh, so no camera. Huh?
No, sir, I can't switch on.
So you are from,
And, sir,
you are from which place?
I'm from Hyderabad only. And, yes, sir, my
Which
father.
area?
It's area, it's near Secunderabad railway station. in Nathipura.
Second. Your father?
He works in a private company, sir.
Okay. Any interests?
So I have a lot of interests.
Lot
Big
of.
list.
Okay. Maybe some priorities may be there, no?
Okay, then I also like games, watching games, not playing games.
Okay. So here in the campus, have you participated in any game?
No, I just watch games. I don't play.
Okay. Thank you, Jvalika.
Thank you, sir.
Ramara is there? I think Shiva Prasad is there. Okay. Shiva Prasad?
Sir, I'm visible. Sir, hello, sir. Good morning.
Good morning. Tell me. From where?
Sir, this is Shiva Prasad from Varangal, sir, near 100 feet road.
Oh, near to the campus or that side, university
Yes, sir.
side?
Near, sir, near to Vadapalli only.
Okay. That is after lake or after
Yes,
the
sir.
lake?
Like at the end of the lake, sir. Yes, sir.
Okay. That Proditory complex. That apartments are there.
Yes,
The
sir. After
Proditory
that,
apartments or something.
yes, sir. After crossing that, you will get one church, sir. 100 feet road, they'll call church.
Yeah. Church is there. Right.
Yes, sir. Near to that.
Near to
Yes,
that.
sir. Near to that.
Oh. So what's your father?
Sir, my father is a heavy vehicle driver, sir. He works in Oman.
Okay. Any interest?
And just like playing cricket, sir, and learning new things.
I think today second match starts, huh?
Yes, sir. ODI, I think, sir.
No,
Not
sir,
ODI,
second
it's
test.
match
South
only.
Africa.
Second test, sir.
Second test.
Yes, sir.
Sai Harsha, thank you. Thank you, Shiv Prasad.
Thank you. Thank you, sir.
Yeah. Sai Harsha.
Hello, sir. How are you, sir?
Yeah, fine. You tell me.
I'm from Tirupati.
Okay.
My father is a teacher, sir.
Okay.
And my hobbies are solving puzzles and watching web series and movies, sir.
Okay. So puzzles, okay, I will ask some puzzles later. Okay. Then Madhu,
Good morning, sir.
good morning.
Sir, I am unable to switch my camera.
Okay.
Sorry, sir.
Yeah, okay. No.
Myself, Madhu.
Yeah.
Basically, my father was a farmer,
Yeah.
and I am an NCC cadet from NIT Varangal.
Oh, very
Usually,
good.
I used to play. I'm a marathon runner, sir.
Okay.
25 kilometers runner.
Very good. Nice.
Thank you, sir.
So you stay near the campus here only?
No, sir. No, sir.
You are from which place?
Sir, I am from Karimnagar district of Telangana state,
Okay.
Jagitya.
Jagatyala. Okay.
Yes, sir.
Okay. Thank you. Thank you,
Thank
Madhu.
you, sir. Thank you, sir.
Hemant, is he there? Okay. Ajay.
Yes, sir. Good morning, sir.
Yeah.
And I am Ajay Kumar, and I am from Hyderabad, sir.
Okay. Which place?
ECIL, sir. AS Rao Nagar.
ECIL. Okay.
ECIL.
So you have to get down at Toppal and go, huh?
Mostly I come through train, Secunderabad, and from there direct bus, sir.
Okay. So what's your father and what are your interests?
My father is in politics, sir. He is corporator now.
Oh, very good. So you have a lot of
And my
influence there?
sir,
You have a lot of influence there?
somewhat, sir, not many.
Okay.
And my interests are playing cricket and watching movies and music, sir.
Thank you, Ajay.
Thank you.
Geeta Sahiti, is she there? No. Avinash. Okay, Avinash.
Good morning, sir.
Yeah.
I am Avinash. I am Avinash from Warangal, sir.
Yeah.
Shenbi Warangal. In Warangal, Balasamudram, Hanmagonda Balasamudram, sir.
Okay.
And my father is a private advocate.
Balasamudram means near the Akshila Park bus stand or something.
Yes, sir.
Yeah. Okay.
And my interests are watching and playing cricket, football, and chess.
Oh, very good. Have you participated any? Where?
Yes, I was in our college chess team. I am in our college chess team, but did not participate yet
Yeah.
due to COVID.
Okay, good. Okay, thank you. There are many local people. 3, I think now.
Yes, sir.
Then Laya is there. I think not yet. Charan Mitra. Rohit.
Good morning, sir.
Yeah, Rohit.
Myself Rohit.
Yeah.
Sir, I am from Vizag, sir.
Vizag, which place?
Sir, at Balaji Garden, sir, near Gopalpatnam.
Gopalpatnam. Okay. Because I worked in NSTL, somewhat near to Gopalpatnam, right?
Sir, I think I know your best friend, sir, Chalam uncle.
Oh, you know him, huh? Very good. Actually,
He
we worked together all the year. We were in the same office, and he was under me.
always speaks about you, sir. That's why.
Yeah, we are very close. Though I am officer and he is a draftsman under me, we never felt like that. And there is a photo of us, and he says, "Sir, I am like officer, and you are like working under me," because he is always very neat and tuck up and the shoes and all. He comes very in a nice way to the office. Okay, I like him very much, and still we are in touch with each other. Okay,
Yes.
convey my wishes if you talk to him.
Yes, sir.
Tell me, what is your father?
So my father works in steel plant, sir,
Okay.
in a QATD department.
And any interests?
My interests are like in sports, playing table tennis, sir. I'm in NIT table tennis team, and we
Oh,
won internet at Silchar. We won the tournament.
okay.
Thank you, sir.
Thank you, Rohit. Jayesh?
Good morning, sir.
Good morning.
Sir, I am from Udaipur, Rajasthan, sir.
Yeah, though we talked, I never seen you. Okay.
Yes, sir.
Right.
Yes, sir. And I love playing volleyball and watching series and movies. And sometimes I do sketching out of interest. And
Oh, very
yeah, my father does a private job, sir.
good. Okay.
Yes.
So if you have any sketches drawn, sometime you can show me.
Of course, sir. Yeah.
Yeah. Thank you, Jayesh. Kapil? Is he there? Okay, then Pranav?
Yes, sir.
Yeah.
Sir, am I visible?
Yeah. Very well.
Yes, sir. So, good morning, sir.
Yeah.
So, my name is Pranav.
Yeah.
Sir, I'm actually a Keralite, but settled in Goa.
Okay.
Sir, and yeah, I like fluids and thermal as subject. So, that's why I chose CFD.
Yeah, good. Hope
So,
you
yeah,
have.
that's it. Yes, sir.
Okay, thank you, Kapil. Okay, Pranav, right. Thank you, Pranav.
Thank you, sir.
Soyab, is he there?
Yes, sir. Hello, sir. This is Soyab.
Yeah.
I'm from Haridwar, Uttarakhand, sir.
From?
Haridwar, Uttarakhand.
Haridwar, okay. Yeah,
Yes,
nice
sir.
place. Yeah.
Interest, I like to play volleyball and cricket as hobbies.
Okay.
And my father runs a hardware shop, sir.
Very good. Thank you, Soyab.
Thank you, sir.
Is Pranay is there?
Yes, sir, he's there.
Is there Pranay?
Sir, good morning, sir.
Yeah.
Sir, my name is Pranay
Yeah.
from Nalgonda, sir.
Yeah.
My father is a businessman, sir.
Yeah.
My interest is playing cricket, sir.
Okay, nice. Thank you, Pranay. Okay, anybody else who has not introduced himself?
Hello, sir. I'm Jayant.
Jayant, yeah.
So I'm from Hyderabad, Telangana,
Okay.
and my interests are like watching movies and also play video games.
Oh.
And my father is a school bus driver, sir.
So Hyderabad, which place?
I live at Godpalli, sir.
Kokatpalli. Okay. Okay, thank you, Jayant.
Thank you, sir.
Okay, thank you all. So maybe we can start our thing. Okay, what do you feel is about CFD? Anybody? Just what do you mean? CFD deals with something like that. Okay, anybody? What is this CFD? You have taken the course, no? So, what do you feel it deals with, and what exactly is
It helps in solving simulations using fluid dynamics.
Okay, very good. And okay, why do you want this?
Turbulent flows.
Okay, so you want to use this only where there is turbulence?
Because there are no general solutions for Navier-Stokes equations.
Okay, why do you want to solve the Navier-Stokes equation? Avinash?
Sir, it's a very
Field and
general form
pressure
of
field.
equation. So if you apply boundary conditions and simplify it, you can use it for repetitive methods.
Okay, good, Pranav. And what I asked Avinash actually is, okay, whatever you are telling also is similar. And why do you want to solve Navier-Stokes equations? Okay, there are Navier-Stokes equations, and
Pressure
we cannot
field
solve with
velocity field.
What, Shiva Prasad? Tell me. Tell me, Shiva Prasad.
To understand pressure field and velocity field in a flow.
So you want to know what is the pressure distribution and velocity distribution, right? And
Yes, sir.
what is the use of it? What is the use of it?
So it has many applications in like daily life, whether it's like a moving plane or it's wind blowing over the building and all. So we want to know like what effects it will have on them, kind of things.
Okay. So what are the types of effects means? You are coming to the same solution, right? The expected answer. Okay, what is that actually you want? So you have flow is there. In nature, there are many flows, and these flows are governed by Navier-Stokes equations. And we want to solve the Navier-Stokes equations. And why do you want to solve is to know the pressure distribution, velocity distribution, or temperature distribution and all. And okay, why do you want to get those distributions? And you are saying there are effects of it. Okay, what type of effects?
Primary effect is
Sir,
force on the object.
What? Pardon?
Primary effect is force on the object.
Yeah, force on the object. Okay, we want to know what are the forces coming onto the object. Okay, so why do you want to know, and what is the use of it?
So like we actually play with these things, like assume like a plane, like we are flying a plane. So what we do is like creating a pressure difference over the body of the plane, and then just make it able to fly. So like we analyze these things and make it happen. So
Okay, that is one of the example. Okay, plane means flight only you are telling, right? Aircraft.
yes, sir. Yes, sir.
Yeah, in the aircraft, you want to know whether we will get sufficient uh, lift and drag and all. Okay, so lift and thrust, I can say. So such things I want to know. Anything else? Yeah, it's right. Actually, we came to the
To
answer
minimize
why
air
we want
friction
CFD.
in automobiles.
Yeah, very good. So the other thing is we want to reduce the friction on the automobile. Okay, that is actually we want to reduce the drag. Okay, I can say, because once he is telling forces, right? So this is like forces, lift force, drag force, something like that. Okay, these forces I want to know. And so if there are two types of drags will be there on aircraft or automobile or these things. What are the two types of drags? Anybody know?
Pressure drag and again friction drag.
Yeah, friction drag and pressure drag. Very good, Jayant. So we have two types of drags, friction drag, so which Shiva Prasad is telling, and Jayesh was telling the lift and other things, and pressure drag. Pressure drag also is there due to when you integrate the pressure over the body, so you will get the pressure force acting on that. So there are two types of drag forces. Why we want to spend fuel? Why we spend fuel on automobile or aircraft? It is to overcome this drag. I have to create thrust which overcomes the drag. Okay, so the main thing is I want to always make it economical, more efficient, and all these things, right? So for that, I have to know what are all the forces coming onto it, and I have to, how much fuel I have to spend to get the thrust to overcome the drag. So for that, I have to know the drag. To know the drag, I have to know the velocity distributions. So that because mu dou u by dou y, that gives me friction force dou u by dou y. So for that, velocity distribution is needed. And if I want to have the pressure drag, I have to know the pressure distribution over the body. Okay, so that gives me pressure drag. In that way, I can find out what are the forces coming onto that. Or if it is aircraft, how much lift force it is needed, okay, to keep it hanging or to have a particular speed. Okay, those things I have to know the forces. So anything else you like to share? Okay, so now whenever there is a flow, okay, so they are governed by Navier-Stokes equations. They are the generalized equations that govern the fluid flows. And as people are telling, we have to find out the behavior of the flow. And there are three ways of yes, 1 minute. So natural flows are governed by Navier-Stokes equations. Okay, what do we mean by Navier-Stokes equations?
So before going there, can you tell what's a natural flow and what is not natural flow?
Whatever flows exist in nature, okay, natural flows means. Okay, they are not like artificial flows, okay, all flows of nature, okay, they are governed by Navier-Stokes equations. Okay, so what do we mean by Navier-Stokes equations? Which equations are called
They're a set
Navier-Stokes?
of partial differential equations formed through conservation of mass, conservation of momentum, conservation of energy.
Yeah. So actually, if you study fluid mechanics, in fluid mechanics, Navier-Stokes equations means conservation of momentum only, if you remember. But when you come to CFD, all the equations that govern the flow together are called Navier-Stokes equations. Okay. So that is conservation of mass, conservation of momentum, and conservation of energy. So these three together, we call them as Navier-Stokes equations. Okay, conservation of mass, there is another name for it. What is it called?
Continuity equation.
Continuity.
And momentum equation comes from which law?
Newton's second law.
Yeah, second law of Newton. And the energy equation?
Bernoulli's.
First law of thermodynamics.
Yeah, very good. First law of thermodynamics. Okay. So solution of Navier-Stokes equations. Okay, what it gives me? Distribution of primitive variables of the flow in the flow domain. Okay, what do you mean by these primitive variables? So what are the flow variables? What are considered to be flow variables?
Pressure, temperature, density.
Yeah. Density, pressure, temperature, and
velocity.
Velocity.
Yeah, these are the flow variables, or these are also the dependent variables. Okay, what are all the independent variables? What are all the independent variables?
Pressure and temperature.
No, these are dependent variables. So
Viscosity.
we were telling that Navier-Stokes equations are PDEs, partial differential equations. Means there will be some dependent variables and independent variables. The derivatives of the dependent variables with respect to independent variables, right?
Space and time.
Time and space, right? We will have dou v by dou t, dou p by x, dou x, dou v by dou y, like that, isn't it? So these are all independent variables, t, x, y, z. If it is unsteady, t will be there. If it is steady flow, only space variables will be there, x, y, z. Okay. So these are the partial differential equations we will have for the conservation form of equations. And if we solve them, we get the distribution of the flow variables over the whole domain. Okay. And Okay, so we want to solve them. Okay, there are three types of methods normally. So initially in olden days, right? So nobody knows mathematics, right? At that time, how do they design actually? How can they know whether
Trial and error.
experiments? Okay, they have to experiment. Okay, trial and error only. We will try with something. We do the experiment, and if it works, it's okay. Otherwise, we have to modify the design. So the experimental approach. And as the mathematics have been developed and people are become intelligent and all, then they use to solve them using analytical methods, which gives the solutions are called exact solutions. Okay, so but it has its own disadvantage because we have studied partial differential equations and all. As long as they are linear, somehow we can manage and solve them. But the Navier-Stokes equations are highly nonlinear. So nonlinear equations cannot be solved using analytical methods. So what we have to do for that? Sometimes the mathematicians try to linearize them with some mathematics, okay, manipulations and all, and they used to solve them. But all of them cannot be linearized. But we engineers are interested in solution. Okay, I have to design it, I have to use it, I have to fabricate, I have to see it works, and such things are there. So people came with what are called as approximate solutions. So I don't bother much about exactness. I want at least approximate solutions so that I can design. So they found that there are methods called as numerical methods. So which solve those equations and gives me approximate solution. And so there normally what is meant by numerical method. You have studied numerical methods also, statistical and numerical methods. So in numerical methods, what we do? Can you just tell me what normally we do in numerical methods? You have learned some bisection method, Newton-Raphson method, regular falsy method, and so many methods like even Gauss
We
elimination.
find an approximate solution.
Pardon?
Oh, we find an approximate solution using the.
Okay, yeah, we find approximate. Okay, how do we use numerical method? Numerical method, what it does actually? Okay, the final outcome is some solution which is approximate.
We know initial and final conditions, and we will find approximate solution in the middle. Something.
Okay, what is the general method?
So we divide the domain.
Iterations.
The equation is derived from the data, sir.
Equations are there. Equations are there, and I have to
Um,
solve them.
Where we assume one value and put it in the function,
Yeah.
and then
Yeah,
come with different solution. We iterate actually in this kind of
Iterations.
yeah, very good. Who is that speaking?
Sir Jayesh.
Yeah, Jayesh. That's what we do. Normally, what we do is I want some variable x. Okay, so I initialize it. Give some value to it, right? And see whether it satisfies or not. If it doesn't satisfy, so you have to find out what is the error. Okay, and then what I do, I update the value with some means. Okay, so you update the value and recalculate error and see whether the error is increasing or decreasing. Okay, so I have to update. If my error is reduced, my updation is going in right direction. So you go on updating and see that the error decrease. Okay, so this is what is iterative process. So find out some iterative process to update X and minimize error, right? So if it is getting minimized, we call it as converging. The solution is converging. So I have to prescribe some minimum error, right? Okay, if it is up to 3-digit approximation, if it is okay like that, and then stop iterating. If the solution is less than that minimum error, I can stop iteration. So that will be the final solution. This is the way any numerical method is used. Okay, so I have a partial differential equation to be solved. I cannot solve it by analytically. So I assume some pressure distribution, velocity distribution, or temperature distribution, and put them in the governing equations and check whether what is the error. Okay, so there are various schemes to update the value which reduces the error. So I have to find out which scheme is suitable for a particular type of problem. Okay, so I have to go on updating the variables and see that the error is getting reduced and solution gets converged. Okay, so that solution, the final solution, is the one which we want. Is that clear what I am talking about? So this is the whole CFD process. And because it is an iteration process, and sometimes we have to do 1,000 times, 1 lakh times, or 1 million times, or more than that also. And humanly, it's not possible. So because of that, we use computers. Okay, so that time gets reduced and mistakes, right? Human mistakes will be there. If you do by yourself, something go on getting repeatedly, if you are doing, you are bound to do some mistakes. But computers, they are sincere followers of our commands, and they will do without any mistake. So that is the advantage. So that is what actually CFD means. Okay, so solving governing equations of fluid flow using numerical methods with the help of computer. Okay, in general, I am telling, okay, what exactly CFD means. Okay, just we will go, because I have made some slides, we just go to that. Okay, Maxwell, he told all the mathematical sciences founded on relations between physical laws and laws of numbers. Okay, all the physics that is going on in nature, okay, all the natural processes can be represented with numbers. So that the aim of exact science is to reduce the problem of nature to the determination of quantities by the operations of with numbers. Okay, so manipulate with numbers, play with the numbers, and find out, come with some numbers or quantities which represent the nature. Okay, so any nature can be studied by converting them into laws of numbers. Okay, here we will see how the importance of CFD came into picture in history. Okay, this is one of the failure story. There is a big bridge, Tacoma Bridge. Okay, it is built in Washington. Okay, on November 7, 1940, one of the most spectacular engineering failures of the 20th century occurred in Tacoma, Washington. During the early morning hours, the Tacoma Narrows Bridge began to undulate violently in 35 miles per hour winds. And after several hours, the oscillations took the form of a twisting motion that would cause the main section of the bridge to tilt it up to 45 degrees angle from its original position. After approximately 1/2 hour of this twisting motion, the main span of the bridge collapsed. The bridge, which had cost $6.54 million in 1940, had been open for only a little more than 4 months. Okay, you can see how such bridge, okay, can oscillate and for a long time. You can see a video is there. Okay, so that is the way it was failed. Okay, that is the first time people thought it is very much important to do some experiments. Okay, so that it can, because it costs you money and also human life. Okay, so luckily it has undulated for or oscillated for a long time period, so that they could evacuate the region. But if there is some traffic is going on and all, there will be a lot of human loss will be there. Okay, this fundamental design flaw in the Tacoma Bridge was a failure. And do you know what is the reason for this?
Maybe they went into resonant frequency with the bridge. The vibrations were occurring at resonant frequency.
Yeah, why these vibrations came?
Due to this
Due to the forces
wind forces.
acting on the.
What are the forces coming out of that? Actually, there is no traffic at all.
The force exerted by the fluid on the bridge.
Which fluid?
A.
Wind.
On the fluid on the
Wind,
bridge.
sir.
Any fluid on the bridge?
Wind only, sir. Wind forces.
Yeah, wind forces. Okay, why wind force? Okay, normal uniform flow is there, and why should there be oscillations? Anybody? Have you heard about von Neumann vortices?
Yes, sir.
What are they?
Behind a bluff body or a streamline body, whatever it is, when the flow passes through around it, an alternating vortex above and below the central line of the body forms.
Okay, why it actually forms? Why it comes?
Due to any small disturbance at the trailing edge, sir.
Okay, actually, when there is a flow over a body, suppose if I take a bluff body like this, and if there is a flow like this, and if it is an ideal flow, it comes like this and goes in this way. Here, what happens? What is this point called as? These points?
Stagnation point and
stagnation points, where velocity equal to 0, pressure is max. And here at these points, I have maximum velocity. Okay, so there will be 0 velocity here, accelerates, and then it gets decelerated like that. This is an ideal flow, and everything symmetric and all. Okay, but ideal flow means what?
No viscous effects.
Inviscid, incompressible. Okay, so if you remember, these are governed by Laplace's equations, del square psi equal to 0, del square phi equal to 0, right? So psi is stream function, and phi is, anybody?
Potential function.
Velocity potential. Okay, so if I solve del square psi equal to 0 in this region, I can find psi everywhere in the field. Okay, if I know psi, how do you find out the velocity? Anybody knows?
U is equal to minus dou u minus dou psi by dou x.
Dou equal to minus dou psi by dou x. Okay, the symbols may be alternate. Okay, some books will have minus here and plus here, and some books will have plus there and minus here. Okay, the derivatives of stream function in x and y directions will give me the velocities in the x and y directions. So I can find out the velocity, and once I know the velocity, because ideal flow is governed by Bernoulli's equation, I can find out pressure also. It will give me pressure. Okay, solving Laplace's equation of this del square psi equal to 0 give me psi. Finding out the derivatives will give me velocities. And using the Bernoulli's equation, I can find out the pressure over the whole body. Okay, and interestingly, here what happens is because of you can see everything is symmetric. Okay, so if I try to find out what is the vertical force acting on the body, suppose if I take like this, so there will be pressures acting in this way. And if I take a vertical component, there will be some downward force. And if I take this integral of this pressure force, there will be vertical force. And because of the symmetry, the vertical force will be 0. That is, lift is 0. So what is lift? The force normal to the flow. That is lift force. So the net lift force will be 0. In the same way, if I want to find out what is the horizontal force coming, if I take a vertical line like this, and if I take horizontal components of all the left side things, there will be some force coming here. And on the right side, there will be some force, and both will be same because of the symmetry. And this force is called as drag. Am I clear? That is force in the direction of flow. This is drag. This is lift. So this is what is called as D'Alembert's paradox. Have you heard about this? Anybody heard about this?
Yes, sir.
What is this?
In an ideal fluid flow, there wouldn't be any drag on the object, but in a real case, there is drag observed.
Yeah. The net force on a long, infinitely long cylinder, I can say, infinitely long cylinder kept in a uniform flow will not experience any force, any net force. So the net force on a infinitely long cylinder kept in a uniform flow is 0. But so what happens if you stand here? There is a flow. You are like a cylinder only, right? So if you stand in the flow, will you experience any force of the air or not? If there is a lot of flow, so you will be pushed back, right? You will feel that.
Yes, sir.
And so actually this is theoretical result. And so people found that it is impossible. It is completely not practical and natural. So they started rejecting the theoretical solutions. Okay. So actually the experimental science of fluids is called as hydraulics. And analytical science of fluids is called hydrodynamics. So all these analytical solutions, solving the stream function, getting the velocity, pressure, all those things, it is called hydrodynamics. So these people used to work independently, experimental people and theoretical people work independently. And they never used to accept the one or the other because of the egos and other things. So they say hydrodynamics is waste because you are getting completely impractical results. So in that way, there is no proper coordination between these two. Actually, there should be. And finally, in 1904, okay, Prandtl came with what is called as boundary layer theory. Okay, what does this say? So if I keep here like this and it is like this, okay, so though everywhere the flow here far away from the cylinder, the effects of viscosity are negligible. And we know that tau is equal to mu dou u by dou y. So the viscosity may be very small, And here everywhere the viscous effects are negligible. And because everywhere the most of the field it is negligible, people thought I can neglect the complete effect of viscosity. But what he said is, near to the cylinder, there will be what is called as no slip condition. Anybody knows what is no slip condition means?
The
Relative
fluid at
velocity
the
of fluid and
surface.
body is zero.
Relative velocity between the fluid and the solid will be zero. So means the fluid here adjacent to the cylinder will not have any velocity. But immediate to that, there will be some velocity, right? So some layer it sticks to that with zero velocity, but immediately there will be. So because of that, there is what dou u by dou y will be very large. So here there will be a boundary layer formed. So here there is zero velocity, but with a small distance, there will be free stream velocity. And because of that, dou u by dou y, though mu is small, dou u by dou y will be considerable and tau will be considerable. So what happens is, so initially when this is zero here and maximum velocity here and zero velocity here, there is increase in velocity and decrease in pressure from this point to this point. This is what is called as favorable. Anybody knows what is favorable?
The pressure decreases in the direction of the fluid flow.
Yeah, this is favorable pressure gradient. So it behaves in a very well, because if something is pushing you, you can comfortably cycle or run in that direction. But from here to here I have the maximum velocity. Now in this direction, there will be velocity decrease, right? And pressure increase. And this is called, what is called as?
Adverse pressure gradient.
Adverse pressure gradient. Because something is opposing. So here what happens is, if it is inviscid flow, there is no problem. But in the viscous flow, this acceleration will not be sufficient because of viscous forces, friction, that tau, right? It will not accelerate to the expected maximum velocity at the top. So it will not have sufficient momentum and acceleration. So if it has to go in adverse pressure gradient till this point to other stagnation point, there will not be sufficient energy. Am I clear? So it is like water, it has to go upflow, means it cannot, it will find out some other way. So in that way, it cannot go in this way, it gets separated like this. Okay, due to viscous effects, it will not stick to the cylinder throughout the cylinder surface. So after the top surface, it will try to get separated. And this is called as wake. And this separation will have vortices, okay? Because there is, whenever there is two layers of different velocity, it will form like a vorticity, right? So here, if this is a larger velocity and this is smaller velocity, so it will try to rotate like that, okay? So it like this. So it forms a vortex. So here a vortex and here a vortex like this. But somehow some tricky thing of nature, still people don't know why it happens. These vortices from the top surface and lower surface, they will not form at the same time. There is a time lag between them. So here it starts, it goes, the vortex forms, and when it goes in the flow with the flow, and after some time there will be a vorticity from the lower surface, and then it goes, and again there will be another one like this. Okay, there will be alternate top and bottom vortices will form, and they will go away like this, number of vortices. So you can see that if you keep your pen, okay, in a bucket of water, and just if you take it to the right or left, so you can see behind the pen there will be vortices and formed, and there will be disturbed flow, wake. That wake you can observe, and the vortices you can observe. This is called as von Karman vortex street. So what happens when there is a vortex formed in the top surface? There will be a force coming on the downward, And when it forms here, there will be upward. So there will be upward and downward forces will act on that, due to which there will be oscillating force, oscillating lift force acting on the cylinder.
Yes, sir.
Am I clear? So same thing happens when there is a flow over the Tacoma Bridge. So there will be uncommon vortex street, and there will be oscillating force on that, and there will be undulations. And when this frequency matches with the natural frequency of the bridge, so there will be resonance, and there will be increase in the oscillations, and finally it has failed. Am I clear about the failure of that?
Yes, sir.
Okay. So this actually made the requirement, people understood the requirement of doing some experiments on that. The Tacoma Narrows Bridge disaster illustrates two main points: that fluid dynamics can play a role in many critical phenomena outside the traditional spheres of aerospace and mechanical engineering. That analysis of these phenomena during the design phase of a project can potentially save a lot of time and money. And even after Tacoma Narrows Bridge disaster, normally what happens, whenever there is a problem like corona comes, you have to take care of your immune system, and all people say, and you will take a lot of care and other things. And after some time, once the corona everything goes, and again we will be careless. Okay, so because living like that, I have to change my lifestyle. I have to kill a lot of my interests and all, right? So because fluid dynamics is difficult, the equations governing fluid flows are nonlinear and can only be solved analytically in a few cases. Only through scale model testing in wind tunnels, towing tanks, or other experiments could more precise and detailed information be obtained. Given that the number of values available for such testing were limited and that the tests were expensive, many projects that might have benefited were not subjected to fluid dynamics analysis, because experiments are highly expensive and time consuming, and the analytical is found to be impossible for nonlinear things. And so though people know that they are important, so they are ignored for very long time. So this is one of the example. All this has changed in the past few decades with the exponential growth of computer power and the application of computational fluid dynamics. Now, because I have a lot of computers are there, I became expert in numerical methods, and I have somebody to work for me like computer, and its pace and speed, everything is increasing. So the importance of CFD came. The object of CFD is to use computers to solve the previously intractable conservation equations for fluids in order to accurately simulate them. Thus, computational fluid dynamics allows the analysis of fluid flow problems in detail, faster and earlier in the design cycle than possible with experiments, costing less money and lowering the risks involving in the design process. This trend is only likely to grow more pronounced in the future as computers become increasingly cheaper and more powerful, while traditional forms of testing become increasingly expensive. This concept was expressed. Okay, only one thing I want to say, these are called three dimensions of fluid dynamics. So one is experimental, analytical, and numerical. So actually all are interconnected. You cannot just, because I have numerical things, I can work with it. Okay, what is the limitation with the numerical methods? Can anybody tell me?
We don't know if it is correct or not.
Yeah. So you write a program, a code, and if you just eliminate syntax errors, it will give some result. But how do you know whether my result is right or not? Okay, that is the main problem. Okay, so that can be obtained only by comparing with experimental results and analytical results. Okay, if I need the help of experimental results and analytical results, why should I go for numerical methods?
So at least it gives like an idea like where to start.
Yeah, okay. So one thing is
Time also.
experiment I can do on one particular dimension or flow conditions. Okay, and numerical method I will do at that size and conditions and all, and check whether it is giving right or not. Once I know that my numerical method works, then I can change the flow conditions. I can change the shape and size of the flow domains and the bodies that is present in and I can predict the unknown things which cannot be done, because experiments I cannot do too many. I can do one or two carefully and give these are the benchmark results. And numerical methods, when I write, first I have to check with the benchmark result, and if it is working right, then I can predict for unknown uh, calculations and all. I can do that. So that is the advantage with numerical methods. Okay, so CFD alone cannot live. It needs the help of experimental and analytical values for validation and verification. Okay, so it is like you have designed an automobile body which gives me minimum drag. And if you go to a particular automobile industry and say, my design gives me minimum drag and it saves a lot of fuel and all, you can use it. But how can they believe you? They cannot spend crores of rupees, because any small change in the automobile industry, which is an assembly line, so they cannot change even a small thing. It costs a lot. So they have to believe you, trust you. So they say, okay, we have our own profiles are there, the automobile profiles. You tell me whether your results match with this. So that existing profiles he will take, and he will do that numerical experiments and say, okay, see if they are matching with this. If they are matching, then you say, now you modify a little bit here and there. Now I will show you the drag will be minimum. Then they will trust you and believe you, and they can put some money and effort in changing that particular assembly line. Am I clear?
Yes, sir.
Yeah. So now what I do is I want to quickly browse some things, because a lot of things I want to know, I want to tell. But so there are some success stories I will tell you. Okay, one is Himat, highly maneuverable aircraft technology, and the cost of okay. So here, wind tunnel in the preliminary design Himat showed that it would have unacceptable drag at speeds near the speed of sound. Actually, these are called transonic speeds, when the speed is near the speed of sound. So they found that it's not possible to do the experiments or analytical results or anything like that in the process of transition. Okay, so so doing experiments, it is found to be difficult, and analytical is found to be difficult, and so the cost of many have failed. So the cost of redesigning it in further wind tunnel tests would have been around $150,000 in those days, in 1989, and would have unacceptably delayed the project. But instead, the wing was redesigned by a computer using CFD model at the cost of just $6,000, and within a short time. And similarly, this is what is Himat, highly maneuverable aircraft. Okay. And similarly, there is what is called as ICBM. Anybody knows what is ICBM?
Intercontinental ballistic missiles.
Yeah, intercontinental ballistic missile. So here, if you see, the initially, if you want to increase the speed, I have to modify the shape of the nose. Okay, I have to make it as streamlined as possible. Bluff body, we have seen there will be a lot of drag. If it is streamlined, the drag will be reduced. So what happens is, in making it streamlined, people finally got through what is called a sharp nose. Okay, so when there is a sharp nose, if there is a supersonic flow, there will be what are called as oblique shocks. Compressible flow you have studied. So you will have oblique shocks like this. So what do you mean by a shock?
Sudden changes in the fluid properties.
Why it comes?
Due to obstructions in the fluid flow.
So whenever there is a supersonic flow, in only supersonic flow, whenever there is a supersonic flow, and if there is a disturbance or obstruction, there will be sudden drop in the velocity and increase in the pressure, right? And that is within just in microns thickness of that, and that is called a shock. Okay, if it is the shock is normal to the flow, it's called normal shock. If it is inclined, it is called as oblique shock. So here there will be shocks coming like this. So again, just I can tell you, you can imagine, suppose a boat is going in a river. Okay, can you see something is forming like this from the nose of the boat? Okay, in the flow, there will be some region of disturbance. Okay, and before that boat, nothing will happen. And within that, it's like a bow-like thing it will make. Okay, if it is going fast, sometimes it will be near to that. Okay, it is something like that. So this is called as oblique shock. Here there is a sudden drop in the velocity. So there will be sudden rise in the pressure, sudden rise in the temperature. So what used to happen is, the more the nose of the missile sharp, okay, here it will get heated more. So when it gets heated, because there is a sudden increase in the temperature, so it gets heated and it used to get melted. Okay, why it happens actually? So what happens is, when it is going, actually ICBM goes into the atmosphere, outer atmosphere, and re-enters into the atmosphere. When it re-enters the atmosphere, right? So when there is a lot of velocity drop, and that increases the temperature, and that temperature and this temperature, everything, they used to melt the nose of it, and missile used to fail. Okay, so through CFD, they found that instead of having a sharp nose, if you have a rounded nose, because normally people think that to have streamlined body, it should be sharp. But some people found that if you keep a rounded nose, okay, like this, and this shock gets detached, this is called as bow shock. Okay, as I told, if the ship is going, it forms like a bow over that, like this. Okay, so here what happens is, there will be more region between the shock and the body, and the heat that gets released, it gets dissipated in the more amount of the air gets more heat than the body here, and they found that it is more safe to have a blunt nosed body, and they found that this is successful later. So intercontinental ballistic missile, you can study this. Okay, so the Mach number is 20. When it is re-entering Earth's atmosphere, actually it used to get failed when it is sharp nose. So if it is a blunt nose, it is successful. So there are, okay, I can show you the, this is the ICBM. Could you listen to the sound?
Yes, sir.
Okay, that's it. Okay, at first people refuse to believe that a strange new thing can be done. Then they begin to think it can't be done. And then they say it can be done. And then it is done. And all the world wonders why it was not done before. Okay, many times whatever we see now, we say it is simple. But it may take decades to come to this position. And sometimes initially whoever invented or innovated something, people might have scolded or laughed at him and all. Okay, but now we enjoy them. Okay, these are the 3 dimensions of fluid dynamics, and some more visualizations. So this is the interesting in CFD. So the sometimes CFD results, simulation results, are more realistic than the real situations. The real world, if you take visualization experiments and all, right, it takes a lot of effort and all. Now you see how beautifully it comes, the flow like this through a diffuser. See, now a flow falls like this. Okay, how it behaves. In CFD simulation, you can simulate the real world situation so realistically. Okay, so I can show you something more. So this is what is called as bow shock. Okay, supersonic flow or a sphere. This is a bow shock. So this is, you can see the far common vortex street. Could you see that?
Yes, sir.
So you can
Yes, sir.
simulate them beautifully. You can simulate with CFD. See, you can see here, this is the physical one, and this is CFD simulation. See how beautifully it is simulated, right? You don't know actually which is real and which is simulation. It is something like that. Something happened. Okay, these things already we have discussed. You can see here also a real experiment and CFD simulation. These are experimental results and these are simulation results. You can see how beautifully we can simulate. And this is how it is developed initially using ideal flows, then inviscid flows, and then viscous flows, unsteady flows. All these things it is developed with respect to time. Okay, so now we can simulate the very realistic flows. And there are various applications. Where do we use CFD? In aircrafts, in automobiles, in biomedical situations like fluid flow in a heart or lungs and all those things, and chemical industries, right? In processing industries, in furnaces and all, and HVAC in a room when you keep an air conditioner, right? How the flow takes place, which place is better, and what power is needed, what uh, power is needed for that. So all those things in hydraulics, the dams and all in civil engineering. So this is civil engineering, chemical engineering, like that. So power generation, and so you can in the drill, okay, if there is a uh, oil drill, if it is taking place near the drill bit, how it is the mud is going and all, and these are the fluid flow over cooling towers, and the sports also, okay, not only sports cars and other things, even cycling when you do, okay, at what angle you have to bend and how much drag it is coming like that. So why use CFD? Actually, it makes the people life easy for architects, designers, chemical engineers, petroleum engineers, surgeons, meteorologists, safety experts, military organizations, and all these people use for different applications here. And so various applications like CFD simulation in prevention of cavitation. So I was asking where are they are used. I am giving some applications. In rotating machinery, you can see compressor impeller, compressor diffuser, and this is turbine, Francis turbine. And this is the for laminar flow or turbulent flow, how the drag changes for different situations. And the HVAC in within the room, the if there is a cooling air is coming like that, how it is distributed, in which place, the complete temperature distribution. If I know, I can see which places are better to sit. Okay, and this battery simulation, that is cooling of batteries, how it takes place, and simulation of aerodynamics on aircraft, how the flow takes place, and you can find out the forces. And not only that, you can find out the stress concentrations where there can be a failure, and thermal management. Okay, so and pipe and valve simulation, and simulation of electronic cooling. So similar to that, that is if there is a motherboard, you know that I have to cool it. Any electronic equipment, you have to cool it, and which way you have to cool it to make it faster cooling. So many times I want faster heat transfer, and sometimes I need slower heat transfer. Okay, so if it is there, I need faster heat transfer. Okay, and suppose if there is a room, and even if a room opened, so the heat transfer should be slow because it should not get heat immediately. So there should be if there is a steam going in a pipe, I should minimize the heat transfer. Okay, and turbo machinery, CFD simulation and all. And rheology, that is what rheology means. What is science dealing with? Anybody knows what is rheology? The science dealing with the materials or non-Newtonian fluids. Okay, whatever we studied is Newtonian mechanics, where Newton's law of viscosity is valid. Mu is constant. If mu is variable, then it is called the science dealing with is rheology, like plastics, polymers, glass, metals, cement. All these things are non-Newtonian things. Okay, and this is combustion or reacting flows, like a gas turbine combustion chamber. If you have, how to know this temperature distribution, and incompressible and compressible flow with the CFD simulation. Okay, these are various simulations, and so we have to know how the background of various subjects like fluid mechanics, thermodynamics, aerodynamics, heat transfer, partial differential equations, numerical methods, any programming language, and use of commercial packages like that. I have given some references: fluid mechanics, Faxon, McDonald, and Sengel; thermodynamics, Engel and Nog; aerodynamics, Anderson; heat transfer, Engel and Incrotera; and partial differential equations, Krising and Smith; and numerical methods, Chopra and Kennel. And any language nowadays, MATLAB is better to use it. Okay, sometimes we may get assignments, and commercial packages. The popular ones are ANSYS and COMSOL. And various textbooks. These are the reference textbooks, and this is the method of evaluation: minor test 30, mid exam 30, and exam 40, and total 100 marks. And so many reference books I have given here. All are available with me, both soft and hard. You can, if you are interested, I can share with them. And but whatever is needed for the course, I will definitely share with you. And these are various NPTEL courses available. Okay, so many are there on CFD. Okay, IIT Kanpur, Gautam Biswas, IIT Madras. There are Kameshwar Rao, Srinivas Jayanti, and Venkadesan, and Prasad and Professor Sanyas Razu. There are four courses are there, like KM Singh, IIT Roorkee, Suman Chakrabarti, IIT Kharagpur. So many NPTEL courses are there. And there are so many journals. If you want to know the literature, so many journals are there on CFD. So I have listed the journals. And there are so many commercial packages available on CFD. Okay, these are all commercial packages. And these are few milestones in the early history of CFD, how it is developed. Okay, so if you are interested, you can go through them. And the Hall of Fame, the people who were the pillars of CFD, like Navier, Stokes, Bernoulli, Euler, Prandtl, Reynolds, von Karman, Galerkin, von Neumann, Dirichlet, Brian Spalding, Harlow, Launder. Okay, these latter people worked more on turbulence and CFD. Okay, so there are so many people. If you just go through Wikipedia, if you want to know what is the contribution of each person, you can see it. And many of the names we are going to get in your course. So these are, and some CFD quotation. The world is an exciting place when you know CFD. In theory, there is no difference between theory and practice, but in practice, there is. There are 3 rules to follow when parallelizing the large code. When large codes are there, like reacting flows or weather predictions and all, okay, I have to parallelize the code. It says it's a fun. There are 3 rules. Unfortunately, no one knows what these rules are. Okay, and all models are wrong, but some models are useful. Remember that all models are wrong. The practical question is, how wrong do they have to be not to be useful, not be useful? So like there are some funny quotations are there. So these are the things, and I quickly go through the small story before ending it. Any questions till now?
No, sir.
Okay. So we'll have a small story. I don't know, some of the stories might have shared with you in thermodynamics with A section, but B section anyhow, they are new to me. Okay, a rich man looked through his window and saw a poor man picking something from his dustbin, and he said, "Thank God I am not poor." The poor man looked around and saw a naked man misbehaving on the street, and he said, "Thank God I am not mad." The madman looked ahead and saw an ambulance carrying a patient, and he said, "Thank God I am not sick." Then a sick person in hospital saw a trolley taking a dead body to the mortuary. He said, "Thank God I am not dead." Only a dead person cannot thank God. Why don't you thank God today for all your blessings and for the gift of life for another beautiful day? What is life? To understand life better, you have to go to 3 locations: hospital, prison, and cemetery. At the hospital, you will understand that nothing is more beautiful than health. So there, that's what actually we don't understand what are the gifts we have got. Okay, so if you are healthy, you are fortunate compared to even 80% of the people in the world. Okay, so everybody has his own ill health problems. And in the prison, you will see that freedom is the most precious thing. We never see the gift of freedom, right? We are so free. Okay, but still a small thing lost due to parents or the institute or something, we'll cry, we'll complain, and all those things. But how free we are. And at the cemetery, you will realize that life is worth nothing. The ground that we walk today will be our roof tomorrow. We all come with nothing and we will go with nothing. Let us therefore remain humble and be thankful and grateful to God at all times for everything. Okay, thank you. Thank you very much.
Thank you, sir.
Thank you. So anything you can communicate with mail, you can communicate with WhatsApp, you can communicate with phone, right? You can feel free. You have my email address, you have my phone number, right? So everything is there. And anything you want to share, whether it is academic or personal, you can always disturb me, right? So never hesitate. Except that, okay, postpone this exam or postpone the give me marks. Such things should not be there. But otherwise, you are welcome to talk to me and disturb me at any time. You are welcome. Okay. So any difficulty in the class, right? You can always initial classes itself. You have to share with me, right? So that I can modify myself to suit you. And but don't complain at the end of the semester that, sir, I could not understand, I could not follow, or I could not this and that. Okay, that is of no use. You will lose the whole thing. Okay, thank you. Anything else you want to ask? I'm going to send you the detailed syllabus, the lecture schedule, the reference books, right? All of them I will send by mail, and the recorded lecture also I will send, and the PPT that I have used also I will send to you, right? All of them you will get by the mail. If you want to keep it in the LMS, I will keep there, or otherwise I will directly send to the mail. Is it okay?
Yes, sir. Yes.
Okay, thank you very much then. See you.
Thank you, sir.
Sir, stop the recording, sir.
Yeah, stop.